Hello, welcome back to our CSCI 310, our cybersecurity. Okay, so for today's lecture, we will keep on to talk about more like different cryptography. Okay, and just like kind of like extend about from the like we call the asymmetric key, we're using a public key and then private key, right? So we talk about the equation. Okay, so mainly pretty straightforward. So mainly if we need to and encrypt we're using the public key, so we're using the E and N. Okay, and then if we are decrypt using the private key, so it will be D. Okay, so here's the equation you need to remember, and then coming into the slides, in the previous we already go through some key points, and then right here just like telling you, okay, so all the steps, and I already post the assignment, so it's related to the all the encryption method that we covered before. Okay, so it just like cover person. I just changed the numbers and all the steps should be the same. Okay, and then we always like try to find the GCD. Okay, to find it and then just choose the number. In the question I will give you the E, but if you have to choose by yourself, or if you see the question, okay, actually something related to the comment which I can call it is like project, or actually just or more likely more slightly more workload than assignment. So you need to study about all these, like compare all these like different encryption and then find the one real situation case. But later I will post it. Okay. And later when we need to determine it and then find D, okay, and then get the public key and private key. Okay, once we get the pair of the public key, private key, then we are able to doing the encryption and decryption. Okay, so kind of quickly recap what we did, then we move on to our next one, is about the checksum. So for the checksum, is using another one is the mathematical function to generate a set of k bit. Okay, so just around set for n bit. So if we see the two numbers, n should be less than or equals to n. Okay, and a we say the k is smaller than n. So except in some like unusual circumstance, we just provide a check on the integrity. Okay. For the ASCII code like priority bit, so we have the 70 bits. So the 8th bit will be the priority. Okay. So the priority. So for the even priority, so if all the even number of like 1 bit or odd, then will be one the odd number of the 1 bits. Okay, and right here's the example we see. Okay, so let's say Bob receive it. Okay, we have a bit pattern 1011. Okay, 1101 like this. Okay, as a bit. So when we say usually even one. Okay, so right now we have a 6 bit 1 bits. Okay, so the character received is correct. Okay. But of course, here's the thing is we need to consider about checksum if you already quickly realize that, well, some student, like when you watch it, you realize, okay, even though I'm using the even one, okay, so using even, if the 2 bit right here, let's say I change the 0 to 1 and then 1 to 0 and then this one to 0 to 1, and even the outcome is same, it's still maybe 6 bit, but the pattern they are different. Then what happened like this? So it will be like change, like all those like preserve the party. So when we send them, maybe using the odd party, and then if the even numbers of 1 bit, they say, oh, they are not correct, right? So it will still have something still happen, but we need to think about that. Okay. And right here for the cryptographic checksum, we talk about for H and then A to B, and so anything. So if they're like the A, so here's a easy to compute, and for any Y, okay, so they are subset of like a B, so they were computationally feasible. So if we only find it like X is like subset of A, so that's why like if we passing the X into the H function, then we will get Y. So it's a more like computational like infeasible to find like two inputs. Okay, X dash like they're subset of A, and such that X they are not equals the A dash like right here. So they are, and then the function like if we're passing the X into it, and that equals to the X like X dash like this. And as an alternative form, so right here, what right here, so if any given, we say anything is a subset of A, so we will computation flexible for find different um dash right here, so will be subset of A, so such a like that. Okay, and here we have one thing is that about the collision. Okay, of course, like here's a term we will describe about this situation, so many of you will hear about that. Okay, so if they're not equal but we have a same the same output, right? So if we're passing this, so there may be a collision. So we have a called a pigeonhole principle. So if there's a n containers, and for the n+1 object, so at least one container, we have at least like two objects like in it. This one, I think if you're learning math, like math, we talk about a lot about this one. And then in computer science, actually we always using this like to say, okay, if we have a n it's just like pigeonhole, so we if there's like the host will be n, right? So if we have n+1 pigeons, so at least like one of it or will be like have two, okay, like this, like passing through. So if we have let's say if we have 32 files and 8 possible cryptographic checksum value, so maybe there are at least like one value corresponding, so at least like maybe 4 files, because like we have 4, right? 4 times 8 with 32, so right here, so they're right here. And when we talk about the key for the cryptographic checksum, so right here we need to request a cryptographic key. So maybe we use the AES. Okay, so AES is the training mode, so we try to encipher the message, so maybe use the last n bit. So it requires the key to encipher it. That means we try to encrypt it. So using this key, so it's a key that cryptographic checksum. Okay, and for those like keyless cryptographic checksum, so they just like they do not require any key. So if you see pretty commonly SHA 512, okay, SHA 3, they can be the example, or the oldest one you see maybe like MD4, MD5. If you sometimes you see using MD5 is pretty popular. Okay, so all these will be using with the key. Okay, so it's keyless. Okay, so another one is called the HMAC. So HMAC will be the hash-based message authentication code. So they will try to make the key. So those that with cryptographic checksum. So for the keyless cryptographic checksum, okay, and for H we define, so they have a keyless like those like for the cryptographic checksum function, and then they will when they take the data, so they have a blocks of bytes, right, and output those like blocks, and then we call it the L, so those bytes. Okay, this one here is the cryptographic key of the length of B. Okay, B bytes. So if it's short, then they will paired with the 0 bytes. Okay, so if long, so they will hash to the length B, and so far we like this. Okay, so if they have a code the iPad, so right here, so it's like 0011011, so they will repeat like maybe called the B times. Okay, so if we have the 0 OPAD right here, so will be like 01111, and then with the 0, and then repeated by B times. Okay, so either way, and right here HMAC will be like for the ancient, we're passing, we say the cage, right? So the K, and then if we're passing the message to M, so once it is equal, is so either will be a the cadence will be the XOR the OPAD or the iPad right here, okay, or the message itself. So this one is called the exclusive OR. Okay, and if you remember the XOR truth table, so if they are same, so the output will be all 0. Okay, for so once either one of the input, okay, it's different, so they will show you the output will be true. So false, true, true, and then false right here. how about the strength about the HMH? So right here will be really depends on the hash function. Maybe we try attack maybe with have like ND4, ND5, and then SSA. Oh, right here 0 actually is A1, so they can able to recover like partially or sometimes with the full keys. So but now you need to know why for the old method like MD4 501 they actually have been like broken because they are pretty old. Okay. Maybe if you see some encryption using MySQL or something like saving password, they're using MD5, so you're pretty like easy, okay, to book it. And next will be introduce the digital signature. So digital signature will construct that like they have authenticate like origins and then those like content or message. So just in a manner like providable to some like disinterested third party, okay, the judge. So those like signature will from the judge, like we say the on third party. So those sender they cannot deny having those like sending message, right? Sending message. So it's like no verification. So they will limit it to some technical proof. The inability to deny. So once like critical key. So what's I used to sign. And one thing we get like claim in the cryptographic key. So they if they was like stolen or components. So like here we need to like provide some like proof, like legal proof, like probably the required. Okay, right here. And if you think about like very common thing, okay, for symmetric, if you still remember Alice and Bob, you're using it, you try to send a key, right? So we try to send in a message and copy the key to Bob. Okay, so right here, that means the original message and cipher that encrypt using a key, right? And they say, okay, this one is a digital signature. No, because this one you just like using the key. Because like there's no third party to determine whether like Alice or Bob they generate the message. So this is not the way. Okay, so this one you just like the in the communication the protocol using a key. So put the common way. So they need to require a trusted third party. So when we talk about the digital signature, so when they share the key, so with the trusted third party cafe. So if you remember the in the previous lecture, like we the slides at end kind of end of it, we talk about RSA, and then when we sending using the we talk about the CIA, right? So including Kathy. So this is the idea. So at this time, the judge Kathy will be involved right here. So they will try to like get the message, okay, with the key from Alice, and then well here if they are sending it to Bob, right? So actually, right here they will saying, okay, if I give this key to Kathy and then say, okay, when once like Kathy receive it, it can we can recognize it and then think, okay, it's a really from Alice. Then I will send a message like using key the key of Bob and then we return it to Bob like this. So if they're really match, then it's the contract was signed. So it will be like this. For the public key digital signature right here. So basically you will at least encipher the try to encrypt the message and maybe have some like cryptographic hash using it using her like private key. Okay. And then in case of the dispute or like question of the origin or whether change that has made, then the judge can use at least like public key to verify the message came from Alice and then there has not been changed. You know, this one is the integrity. So if you remember, so just like apply what you learn. We change it like digital signature like using same way. So integrity, authentication. So it's the same part right here. So that's why you see this time they be using the private key. But if you remember for the CIA, if it's for confidentiality, so we are using the public key to encrypt, right? But if you're sending using integrity, then this time you encrypt with a private key. So like this. And when we're doing the RSA, okay, so if you remember, like we also like use the RSA for the digital signature. So at least we have a key. So right here with a EN and then the private key and then the D, at least will be a private key right here. So maybe you say, okay, so if we're using E to represent the public key right here, when Alice sends the message to Bob, okay, so if we're using the encrypt the message, you say maybe using the Alice public key right here, and then in the judge we try to like compute then how we're going to use it. So this part we're using the private key of Alice to send the message. Okay, and if there's a message, it's a signed message, then we know, okay, so know who is it from is it from Alice, then we know, okay, it's her, and then from the judge know, okay, it's her, and then we change it to Bob, and we will send it to Bob like this. So we can keep going, and right here, if we're using a private key to encipher a message, so that's why the protocol for use, they're much more like critical. So right here, so we never sign the random documents. So when we are signing, we always like sign with a hash and never like documents. And also don't just like encipher the message and then sign, okay, or just in reverse. So sometimes they will change the public key and private key, so can cause the problems. And also if the message like can be forwarded, then the third party cannot tell if the original sender is sent to her like this. Here will be just an example telling, okay, if we have an attack and like, let's say Alice and Bob, they're communicating, and then we're giving NA, okay, EA and DA, if you remember, okay, and there's like from Bob, okay, private key, okay, so right here, so if Alice asks Bob, okay, try to sign it, so the value, so if she can verify, okay, if she has the right public key above, so maybe you will see the line right here, so inside, so if we're using the audio message, and then with the private key right here, and try to mold the value of like the if you remember the equation, okay, message, okay, and then with the key and get the 22, 55, 36 and power of it, and then mold it to 88 329, so will be right here the Bob's n, okay, the m right here, and try to get a value. And then later when we move on, so she'll ask the Bob to sign the statement, okay, so if sign the statement, and this time we will same with a message and mode MB right here, okay, and here's the statement, here's a message, and we can get another value. So once like Alice try to compute this a new message, okay, so sending and then sending it, so it's just a number, so they will just like showing it's a corresponding like signature, and here's we referring like using the numbers to mode 28, 30, 29, so here's the value. And once like Alice like now can okay, so it's like Bob sign it, okay, so it's the value right here, the message, and it's a proof like supplied signature, okay, and the judge will try to compute like based on the message and current message, so we'll be right here, and then using like Bob's like the E 22529 right here, and then just move Bob's like N right here. So actually we are still like using the same equation, just like we have to fit to a current one, and if the signature they validated, and then okay, so Bob is told like this. And how can we prevent the like attack like this? So try not to sign any like random message, and this will prevent Alice from getting the first message. Okay, so when signing, so we always sign the cryptographic hash of the message, but not the message itself. So this like is a way, and you see like all the numbers right here, but everything will be based on if you remember the equation. So actually just like based on the same equation. This time let's say if like you just need to know who is like asking, who is like signing the signature or getting it for it. So if like we try adding Bob, so we're using Bob's one, and so you see the all the values and then inside the statement, okay, and right here, just like pay attention to like who is sending this one like as a reverse for this time. So if let's say for a Bob and Alice like agreed to sign the contract, okay. So when we only get a value, but this time like Bob want to like her to sign the contract and another one, and but only one thing knows like she won't like, then maybe Alice will try to assign it and sign it. So this time because I get the Bob's content and mold the Alice one, and then we using Alice private key and mold the Alice value. Okay, so right here this time for the message using the contract. Okay, and then here's a Bob's like the private key, and then we mold the Alice, and it's a still so it's a public key value. Okay, it will be the NA. Then it will power of the private key of Alice. Okay, and then move with the Alice. So you see like two layers right here. And so if like Bob change his like public key, so once they try to compute, so it may be we using R saying this time, so we'll be changing. Okay, so 04212 right here about R, and then more 28 329 right here, get a new value. So this time, okay, so it directly get 9175. Okay, and if this time we may try to compute, oh, this one is the bomb, and then modify MB. Okay, so when we put the substitute right here and then move it, and this time we try to replace with the public key, and then just like quickly we jump to it. Okay, so when Bob tried to, just need to know the result, when Bob tried to claim this contract and try to compute, so here just need to find the value. So start with the but right here, so will be like the in the beginning, because the Alice cipher, right? So right here through 2390, and then we going to use the value we need to find, and maybe 54. And if you remember, so right here, okay, and then we move the n and power of the at least like private key. Okay, n, and then this right here, and then we get the value. Okay, so and then we try to see, okay, do they like does it match with the contract EWM right here? So if they verify, then it's okay, and it's toast. So here's another one like doing it this way. So right here you will see instead of like just like encrypting the message and then just sign it, sometimes we need to sign a message and then encrypt it, and it may not work like due to the surreptitious like forwarding the attack. And the idea is right here, if Alice try to send it to the Kathy, so they try to encrypt the signed message, and Kathy try to decipher it, and then we cipher it and with using like Bob's public key, and then send the message and the signature to Bob. Okay, so maybe you think, okay, this one is coming from Alice, right? So they were intended like from him. Okay, for him like this. There are several ways to solve it. Maybe we try to put the sender recipient in the message, and then change the recipient and validate the signature like this. So when they try to send the message, encrypt it, and then sign the result, it also is the possible way. Quickly, we talk about the digital signature, and then if we try to say, okay, but if we doing the attack and then modify here the equation, here same equation we just like fit to giving all the NM, and only one thing like all this telling you, okay, even it match. Okay, so it's like, okay, the value, so you say, okay, it's verified, but only one thing is like, okay, they already change it. Okay, so I do not know actually who they are. So right here, and then we kind of like move on. We be about like summarize to all this that we have the classical and our public key. Okay, classical will be the symmetric, and then public will be asymmetric. So for the classical, we try to decipher the same key, and then public key cryptographic system. So we using different keys. We'll be using public and different private key, and also we have the checksum. and just like check on the integrity. But one thing we need to be careful, because even we using doing checksum, it doesn't mean we can guarantee. Okay, because like we have maybe for even, but when they have 2 bits they change, then maybe sometimes we see some crash. Okay, so that means there is no issue. And also we can use the digital signature to provide integrity of the origin and content. So it's a pretty similar idea like we putting in the previous. Okay, so it's much easier with the public key cryptographic system, like than using just the classical just a symmetric crypto system like this. Okay, and right here we have keyboards. So we have a authentication system. So it's based on this one. Okay, Ham, this one, and they will be like using the central server place role of the trust third party, saying pretty same idea with the third party. Okay, right here. So maybe they have a ticket like issues the runters for identity, and then we have the authenticator, so we'll be identified the sender who know the AI. And the idea in behind, so if we have the user, so try to authenticate, okay, and we will obtain the ticket, okay, try to get the ticket from it, and for the ticket granting service, if we want to use the service, then we need to send the authenticator and then with the tickets to it to ask for the service, and then it will send the tickets to the user. So you can send it, okay, with your authentication and then with your ticket to the server to request to use as something the service. So here's the idea in behind. So overall, like just like the step, here's the graph is showing the structure, the flow, okay, from the user, and then we quickly send to request it, and then return it back with the ticket, and then we can send it to the request it to the TGS right here, and then we reply back service ticket, and then finally we can go to service server. So here's the flow. It looks like. Okay, and pretty straightforward. And for the key generation, so mainly we try to want to like just like it's difficult to guess. But for the problem, because we want to get the like set like k potential keys and just choose it randomly, or just like choose one. Okay, so just like between, okay, then why is hard? Like the difficulty, because when we try to generate a random number, so actually it's like maybe is the called a pseudo random. We always really not really generate a random number. So it's like this. So when we say random, because like when in the sequence of cryptographically like random number, they just like given a sequence of number. So like 1 to like n to somewhere. Okay, so we not really like maybe the observer cannot really predict like nk. So even if like from n1 to like nk means there or no. So physically, so we kind of like for the source the randomness, okay, because we have a random pulse or maybe some electromagnetic phenomenon or like characteristics of some commutation environments or and background noise or something like here. And when we talk about like the pseudo random right here, because all those like the sequence of number they intend to simulate. So we talking about those like cryptographically random number, they actually just generate by algorithm. So it's really hard to do this because like when we have a linear like congressional generator, so if we balance to it, so maybe they already like broken or like for the polynomial congression, so like generator, so they also like already broken. So basically of them they really kind of like broken. So that means the next number is they always get able to be like determined. So it's really hard to tell. And if we want to provide the best way of it, so maybe we try to mix like some functions, maybe like two or more input, and then we try to like output it. So it depends on some like nonlinear function. Okay, so here's some example AES, SHA 512 or SHA 3. So right here, so maybe we can do it in this way. And here's a quickly. And next way will be the biometrics. We can like physical like some variations right here can cause a slight difference. So maybe unique. So it's good source for randomness. So for this one, maybe using the least significant bit of the data. Okay, the biometric for the journaling the keys. So maybe like they tie to the individual. Okay, so maybe need to get a survey analysis to determine them, but they must be like we generate consistently. So we need to know. And when we represent those data, so should be a bit string, okay, and we need to transform them, okay, those like data to some way, and then generate the cryptographic key, and we need to add some like randomness. So if those like key they are compromised, and we need to new or different one to create. So for the biometric, okay, and the idea for this one, the cryptographic key like infrastructure, so we need to bind the identity to the key. For symmetric way, it's not possible because all the key they are like sharing. So if we use the protocol to agree then on share key like this, but if we're using the public key asymmetric way, so like we bind the identity to the public key. So kind of crucial if the people they're using those key to communicate. So based on the principle, so we need to know like identity and then the erroneous. So this one like binding. So means I know sincerely like between the principles. So also we need to assume those like identity like by also acceptable names, all these. And next we have the certificate, and we try to create a token contain the of course the identities and those like public keys and then timestamp and also other information. Okay, what's the identity of the sign like this, like signed by the trusted authority right here. So including, so here will be the key and this, okay, and then with the timestamp, and then with the key we're using Kathy. Okay, so this one we like totally encrypted. So like for Alice right here is the idea of using the certificate. And when Bob tried to get the Alice like certificate, so if he knows, okay, this one is a Kathy's proper key, so he can decipher the certificate. Okay, so maybe we know, okay, when is this certificate issue, or like is this principal user is Alice like this. And also Bob has like Alice proper key right here. And because like Bob needs like have this like proper key to validate the certificate, and it will also push up to a level because we need to know, okay. And we have two approach. So you can think about that. And right here, when we try to create the certificate signature, so we have like two certificates. So we need to generate the hash of the certificate and then encrypt the hash with the issuer. That means a Kathy's private key, if you remember. And then for validate, then we need to get the public key and then decrypt it. Okay, and we compute the hash from the certificate and compare it one more time. Okay, so it's the same. Then how can we get a public key? So we also like for this one chain. So if you look at it, this one like including for the X like 5 known chains. So if you're interested, you can look at the browser and go to when we have all the certificate, where the version, serial number, signature, algorithm, all this information you can find from the examples. If you go to all the website and with the certificate, okay. So with the TLS, SSL, and then all the certificates, so you see the issue version. If you're interested, you also can go to the British Campus website, official website, click on it, and you can see. And then for this, the X509 certificate validation, so first we try to obtain the public key. Okay, so from the same algorithm, and then we try to decipher the signature. Then we will get a hash of the certificate and try to recompute it one more time and from the certificate and compare. So if they are different, then there should be some problem. And maybe we try to check the interval of validity. So we try to confirm the certificate is the current one. always try to match it. And for the issuer, we always say we have the called the CA. You see a lot of certification authority. So this one with the entity that issue the certificate. Okay, so this one of example we use maybe called the Let's Encrypt is free. Okay, and for this also sometimes for the you need to get the certificate, you have to pay for it like to validate like who you are. Okay, and we have multiple issuer. Okay, so post the validation problem, and but at least maybe this time the situation is like Kathy, and maybe let's say Bob is like the CA is done, then how can we validate Bob's certificate? Then we still need to think, okay, maybe they have a course certified by those like certificate from each other's like this. So there's still some okay. And another one will be the PGP change. So this one will be the certificate structure. So they will make it a package. So they're from public key packet. Okay. So either they maybe have 0 or more signature package. So in this like public key package, it comes with the version 3, 4. Okay. So compatible. So of the other version like for 3, and if 4 then is cannot compatible for the older version. Okay, it connect all the time, and then validated them is like version in the version 3, and also we have the public key algorithm, and then come with the key. So like this, and here's the kind of like some contents letting you know. So what's the including version, signature type, creation time. Okay, right here. And for version 4 is getting more complicated. And when we talk about signing, because like for signing, so if for those like certificate, they have multiple signatures. Okay, so the notations of the trust, so they are kind of like embedded in each signatures. So those like range can be like from maybe untrusted to ultimate trust. So right here they have different level, just like right here maybe therefore like more version of 4 keys. Okay, signed by a subject of the certificate. So we can go to self-sign, and self-sign can be like as what I mentioned, like Let's Encrypt is one of the example you can use right here. And how it really work, and this part like okay, so if I need to if you remember talk about the OpenPGP cert, right? So if we need to validate, so maybe we don't know like with that like friend like this, then we maybe here showing okay for the self sign maybe like not really show right here. So once you get the cert, so maybe if you know maybe here right here hurry is very slightly, and the signature is casual level of trust, and from Alan's cert, okay, knowing it of Jack too. So when using like his cert to validate Alice one, so and then we can like validate that Bob. So actually right here you see the change. So we just like trying to, if I want to validate Bob, then we try to like go through others like just the cert. Okay, so going okay, if let's say from Jack, and then right here Henry like this, and then GCI right here. So will be also pointing to Bob. So they are all possible way. And then our public key infrastructure PKI. So those like infrastructure. So that's like they will manage those the public key and certificate of authorities. Okay, so this like including that all those like registration authorities and other entities. So they're involved in creating and then issuing the certificate. Okay, and here are just more details about the XL509 the PKI. This like so it's an entity certificate. So this certificate will be issued like to the entity. They're not authorized to issue certificate. Okay. So those certificate authority certificate so will be let's say issued to a CA. Okay. And self-issue. So the issuer they are not on the subject, and they are the same entity. And then for self sign will be the self-issue from the self-issue certificate with the public key in the certificate. So they can use it for validate the certificate digital signature. Right here you see they come together. Okay, and then we have got trust anchor. So will be like we know the begins of the certificate signature chain, and then we have the cross certificate. So the certificate will be one of the CA issued by another CA. So we knowing each other's, okay. And then registration authority, so the entity delegate. So the registration task by CA, and the CA will trust the RA registration authority. So the identity of the cage, whether the entity is over here. And here, like the basic is like for any PKI. So they like is trust, but like when we try to trust that the binding identity to the public key, so there should be like correct, and then we need to think about degree of the confidence that really be depends on the CA or the RA. And then when we trust the public CA, we issue the certificate. So maybe the insurance policy and also implementation, the signing like this. And the certificate then they don't know really like embody the authorization, so maybe the identity. Okay, so many of them, but they're the external to the PKI. So they may be if you try to trust like two certificate, we have like same public key. Okay, maybe the private key so comes together. And we try to like storing the key. So multi-user or the network system, so the attacker may try to defect according those like control mechanism. So when we try to encipher the files containing the keys, so they will try to monitor those like keystrokes to decipher files, and then those key may be like Western in the memory, so they maybe try to read it from memory, or like maybe using physical device, the smart card, so they will never really enter the system. Then you can store this card. Okay, then you have two devices combine the bit to make the single key like this. And we have the key escrow system. Okay, so they will allow the authority third party to we cover the key and useful when the keys that belong to the role or something like the system operators. Okay, and then also the business, they can recover their backup key or some like law enforcement, so they can recover it. Okay, when they need it. Okay, so we're controversial. So trying to provide a desirable like properties. Okay, right here. So just like let you know, they are not really depends on the encipher algorithm and those like privacy protection mechanism. So they must like work from end to end and part of a user interface and requirement they must like map to the key exchange protocol and support the key as work code must be require other parties. Okay, and if the message they are observable for a limited time, then the system they must ensure the key they are valid. Okay, and also we can do the identity based like encryption. So they will maybe they publicly know the identifier. So they will like their public key. So those like trust third party. So they can use those as a secret like to use the public key to destroy. Okay, so it will be like that. And then for the trusted third party, if they're using the provider a secret, so they can use their public key. Okay. Sorry. Okay, so there's a trusted third party, so they can like decipher a private key, so they know there's a secret, and then or there's the private public key. So others cannot like as what they do not know the secret, and also they can use it in the system, so they can compute with the third party. Okay, so as the escort agent, so it will be like this. And keep going the properties. So those like public keys, the crypto system, so they must like meet the following. So private key should be easy compute, and then also the computation and the invisible to the compute private key from the public key. Okay, and then we need to also one thing the RSA, so they cannot satisfy the both conditions. simultaneously. Okay. For other method, like if we try to meet this condition, then we just need to think about the if they have argument to provide the global SQL key to decrypt any ciphertext, or the encrypted using a public key like this. Okay. And for the key revocation, so if the certificate invalid, so before the expiration, so maybe they need to usually maybe they have a compromise key, so maybe like change of the circumstance somewhere living, then maybe they need to revoking the certificate, right? So they're authorized to do so, and then like revocation, so those like information, so they will circulate to everyone fast enough, like try to do it. Sometimes we have done some like network delays, infrastructure problem, so that cause a delay. Right here we give adding it CRLS, so will be the code certificate of revocation list. So this one will be a list with the certificate revoke. So we add it to the XI509. So this adding to it, and also the PGP. So the signer can like revoke the signature, owner can revoke the certificate, and also allow others to do that. So it will be like can add it to it. And kind of like end up with all this. So the last part we talk about the key management. So right here, and we will say the keys, they need the infrastructure to identify the holders and allow like revoking, and it's just like complicate to the infrastructure. So like this. And kind of like wrap up everything. So we talk about the RSA and then introduce the we have a certificate, right? So, and also of course, like I would say, we come with the checksum, and then we have the certificate. Okay, how can we like sharing certificate like this? Also we have the signing it, and then we have the X 509, the standards right here, and then later with different type of like encryption, like identity base right here. Okay, and then key. And then how can we store the key also right here? And when we're sharing the key, then we need to think about it, because even we try to have a trusted party, and how can we make sure, like how can we get the public key from our trusted party? Okay, so all this will be the consideration. So far, like quickly go through all the encryption, and just letting you know later we kind of like composure, but it's more like you need to have a discussion, think about, okay, so what kind of thing about the encryption, or you have to pick the one discuss. So it will be kind of like pretty similar to the what you did about the virus, like those like is the topic. And I will post it in the next week, so you have some time to prepare for it. Okay, thank you.